Hello everyone, welcome to today's video on non-negative least squares. I'm pretty sure maybe you have heard about the name of this algorithm. It's widely used in genomics, bioinformatics, etc. So if you have heard about linear regression, then this is familiar, but there are some additional constraints involved here. So in this video, I'm going to show you the applications of this, and also I will show you the entire algorithm of how to solve this problem of NNLS. So let's dive in. So first, let's see the least squares regression that doesn't have any constraint. I mean, any non-negative constraint, basically. So you can see that we have two vectors right here. This is the first component, and this is the second component. And there are some coefficients x1 and x2. We have to add these two things up to make this third vector, right? Now, we don't know the value of x1 and x2, and that's what we have to find out. Now, we can rewrite this entire system using matrices. So this is a matrix, and the columns of this matrix are these two components. And then we have this x1 and x2 in the x variable, the x matrix. So this is a simple column matrix. And finally, we have the y column vector, right? So ax equal to y. I mean, that's what we have to do. But now, obviously, we don't know the value of x1 and x2, and we have to solve for it. So the goal here, the loss function here, is to minimize this ax minus y whole square. So if we can find ax perfectly, then this is going to be 0. So obviously we know that if we want to minimize some loss function, we have to differentiate with respect to the variable. So here the variable is x, so we differentiate with respect to x and set it to 0. And if we solve the equation, then we are going to get this nice closed form. And we can actually fill in the value of a and y in this closed form, and we can get the value of x, right? x1 and x2, that means. So it is as simple as that, but this will be the solution for this problem. So 4 by 3 and 1 by 3. But there are some issues here. For example, I mean, x1 and x2 are unconstrained, so they can be anything. They can be negative values as well. It could have been minus 1/3 or minus 4 by 3 as well. So it doesn't matter. But there are some problems in which we don't want these coefficients to be negative. We strictly want them to be either 0 or positive. So I'm going to show you an example of that right now. So that is where we actually show non-negative least square regression in an LS. So here, all the x's or all the coefficients have to be greater than or equal to 0. So the example is this. So you have 100 gene expression values for these three cases: immune cells, stromal cells, and tumor cells. You know each of their gene expression value for the 100 genes. And also you have the same gene expression value of 100 genes for an unknown bulk sample. What you have to do is you have to know the possible mixture of these three cell types to construct this unknown bulk sample. That means what is the percentage of immune cell there in the bulk sample, the percentage of stromal cell, the percentage of tumor cell in the bulk sample. Now, obviously, you know that the fraction of percentage, it cannot be negative, right? It always have to be positive. So this is where NLS comes into play. So you can see that this is how we can construct the problem. So we have the immune, stromal, and tumor cell vector, and they will constitute the bulk sample, and they are being multiplied by the coefficients x1, x2, and x3. And they can be formulated into a nice vector like this. So these three are formulating the A matrix. This is the column matrix. And then we have the Y. And similarly, we have to minimize ax minus y whole square. But this time we have an additional constraint. Now the issue is this constraint that we just specified. I mean, if we specify that constraint, we cannot really have a closed form, nice closed form for x or the coefficients. So we have to actually use some iterative algorithm called Lawson Hanson NNLS algorithm. So I will describe it now. So first of all, you have to initialize. You have to initialize all the x's to be 0. They cannot be less than 0 since negative weight is not allowed. The next thing is to maintain two sets for these variables, an active set and a passive set. So initially, active set will contain all the weights or all the coefficients, that means x1 to xn, and their value will be 0. So initially everything is 0 and they are put to the active set. And the other set, which is the passive set, it will remain empty. What we are going to do is gradually we are going to put variables or the coefficients into the passive set. So whenever we see that some variable is actually going to be positive, so it has a positive impact on the output, then we are going to gradually put them to passive set one by one. So then we have to do gradient calculation to actually find those variables that will be gradually positive. So let me first motivate you why we need the gradient. So let's see these two cases. Suppose we have only one coefficient, that is x1, and we have this loss function L. Now, if we simply like move this x1 around this axis, so if we just change its values, we are going to have different losses, right? We are going to have different losses based on those changes, and this is the optimal value for x1. This is where we want to actually go to. Now, let's say we have this point x1 bar, so where x1 equal to x1 bar basically. So now obviously we want to move to the negative direction in order to reach this optimal value, right? So this is, I think, very clear seeing this loss function and this picture. Now, the tangent or the gradient at this point is a positive gradient, and we want to move to the negative direction. So bear that in mind. Similarly, if you look at this picture right here, so here you can see they have x1 double bar, a particular value of x1. So in this case, we want to move to the positive direction, and here the gradient or the tangent, if you draw the tangent in at this point to the L loss function, it is going to be a negative gradient, right? So basically, we have to move to the opposite direction of the gradient, and the gradient also gives us the magnitude, like how much we have to move x1, right? So this is why we calculate the gradient. So this is the loss function, and this is the gradient del L del x. This is basically the gradient. So you can do the math here as well. I'm not showing you the math here. Now we are going to set a variable w, which is the opposite of del L del x, because as I told you before that we are going to move to the opposite direction of the gradient. So w, we calculate w. And so now xi, any variable or any coefficient xi will be updated in the same direction and magnitude as wi. So basically xi equal to xi plus wi, you could have done that. That is what I'm trying to say here. Okay. Now, after you calculate the gradient, then we have step 3. We have to add 1 xi per iteration to the passive set. So what does that mean? So obviously you have the wi's for all the xi's now. And obviously those wi's has to be positive. Otherwise we are not going to like do what we want to do here. So what you have to do is you have to look at all the wi's. You have to choose the wi with the highest positive value, and that xi will be moved to the passive set. Why? Because obviously if you have a very positive high wi, then xi is going to be updated in the positive direction, and obviously it will have a large positive value, which you want, right? In NNLS, you want the positive coefficients. So this is, I think, very clear. So now you push this xi to the passive set, right? So now xi has been moved to the passive set from the active set. Okay, that's cool. So this is to understand that in iteration number 1, only the top xi, like only one xi will be in the passive set, in iteration number 1, right? In iteration number 2, we'll probably have another xi moving to the passive set, so 2 xi. The iteration number 3, 3 xi. So, so on and so forth. We are going to gradually move these variables to the passive set, right? Now, obviously, this is very important. We are not going to update any xi in this step. So there is no update here. It's just moving to the passive set. Now, we are going to update using the normal least square regression to solve for passive set. What do I mean by that? So suppose x1 and x2 are in the passive set after this is step 3. So obviously you can make these two matrices. So we have the two columns a1 and a3. So a1 and a3 are the column vectors with those passive set coefficients. And we can actually construct this nice equation, and we can use this closed form to solve for xp, right? So we know the value of xp right now. Obviously, these are passive set x's, right? Because I'm saying xp. That means they're from passive set. x1 and x2 are from passive set. So there is no update for the variables in the active set. That is the important thing here. So you have moved variables to passive set, you have updated those variables, but now what? So you can see that this is normal least square. That means there is no constraint. So unluckily, one or two of your xp's or a passive set x's can become negative as well. In that case, what are you going to do? So handling negative xp, that's the next step. So you need to do one more round of update with appropriate step size to make sure all xp greater than or equal to 0. So you can basically calculate some step size, and you can just update all the xp according to that step size in the positive direction, so that they remain positive basically. They don't become negative. So obviously there will be one xp that had the most negative value. That means it's the worst of all, right? So you are going to put that in the active set again, right? Because active set contains the variables which we want to be 0, which we want to remain as 0. So you move that to the active set. So finally, you have the iteration. So we know step 1 to step 5. So you are going to keep repeating the steps from step 2 to step 5. Step 1 was the initialization. It will be done only once. So you need to update from step 2 to step 5. So what are the steps? You keep adding new variables to passive set through gradient calculation. you calculate their appropriate value using unconstrained least square, and you handle the negative passive variables for following non-negative constraint like this. So you keep doing that, you keep iterating until none of the wi calculated in step 2 is positive, because in step 2, if you see all the wi are negative or 0, then you can no longer actually bring any xi to the passive set. That means all other xi will remain 0, and the xi will remain 0, meaning that they will be in the active set, and the xi's that are in the passive set will obviously not update anymore. Basically, they are already in the passive set and they have the positive values, right? You have already solved them using the unconstrained least squares. So you have some 0x x's and you have some positive x's now, and that's it. You are done. I mean, you can no longer bring any xi from 0 to positive. So that is all for today's video. I hope you like the video. If you like, please feel free to subscribe and share. And we have a donation link in the description. Feel free to donate as well. Thanks very much.